So welcome everybody to the 65th annual G.N. Lewis Memorial Lecture, which was established, of course, in honor of Gilbert Newton Lewis, who served as Dean of the College of Chemistry from 1912 through his retirement in 1941. He did take a couple of short breaks for sabbaticals in that period, but I think it's safe to say that that record of longevity will never be broken. Certainly not by the current occupant of the Dean's office anyway. Now, as all of you know, G.N. Lewis was a towering figure in the field of physical chemistry, known for the elucidation of the chemical bond and the role of electron pairing, not to mention the concept of Lewis acids and bases. But G.N. was actually much more than a brilliant physical chemist. He was the person primarily responsible for establishing the international reputation of the College of Chemistry. He had a pretty good eye for talent. Many of the biggest names in chemistry, including Hildebrand, Pitzer, Latimer, Choate, Seaborg, and Calvin, were all recruited by G.N. Lewis. And if he'd had a chance, I'm sure he would have loved to recruit today's speaker, Professor Robert Bob Bergman. A few words about Bob. Growing up in Chicago, Bob attended Carleton College, where he edited the college newspaper and considered being a journalist before finally setting on a career in chemistry. Basically, Bob could have done anything he wanted to do, and we're very happy he chose this path. He earned a doctorate in chemistry from the University of Wisconsin-Madison and was a NATO fellow at Columbia. He then spent 10 years on the faculty at Tech before moving to Berkeley. He is currently the Gerald E.K. Branch Distinguished Professor Emeritus and Professor of the Graduate School in the College of Chemistry. I could talk at great lengths about Bob's research accomplishments. We'll keep this fairly brief. He is a trailblazing researcher who has made truly seminal and significant contributions to both the organic and organometallic chemistry of hydrocarbons, including creating the first transition metal complex capable of breaking carbon and hydrogen bonds. Throughout his career, Bob has been a pioneer in taking the methods and reasoning of physical organic chemistry and using them to help grow the field of organometallic chemistry. His work has revolutionized the field of CH activation, one of the holy grails of chemistry, and he continues to expand our insights in this area, providing the foundation of organometallic chemistry as we know it today. The author of more than 500 papers, Bob has been recognized with numerous major awards, including, to name just a few, the Wolf Prize, the Welch Award, the DOE E.O. Lawrence Award in Chemistry, a Guggenheim Fellowship, the U.S. National Academy of Sciences Award in Chemical Sciences, and several major ACS awards. He is a member of the National Academy of Sciences and a fellow of the American Academy of Arts and Sciences, the American Chemical Society, and the American Association for the Advancement of Science. Bob is also an outstanding educator and is committed to science education with distinguished teaching awards from both Caltech and Berkeley. And Bob, you may be the only person who has that distinction of teaching awards from those two institutions. His course in physical organic chemistry has become a classic in the department, and through it, Bob has developed a number of novel interactive teaching methods. Finally, he has mentored over 250 graduate students and postdoctoral fellows during his career, many of whom have gone on to have their own storied careers in academia and industry. And finally, Bob's service record at the university is unmatched and far too extensive to recount here. Let me just point out that he received the Chancellor's Award for Public Service, awarded for his catalytic role in a highly successful collaboration between UC Berkeley graduate students and local school children in promoting science education. In all, Bob Bergman has not only changed the way people think about hydrocarbon chemistry, he has changed the way people think about science and about science education, much as G.N. Lewis did throughout his career. So please join me in welcoming this year's G.N. Lewis lecturer, Professor Bob Bergman.
trouble with introductions like that is that you have to live up to them, which I will try to do. I'm not sure how successful I'll be. Thank you, Doug, for very kind words. Thank you all for coming. I'm sorry that we're squeezing everybody into this room, which looks rather tiny today. But as all of you know, trying to find a room to have a talk with this much potential audience is almost impossible at this time on a weekday. So I really am grateful for your forbearance for sitting on places other than chairs. So I thought about a lot of different things to talk about today, and I decided that maybe the most appropriate thing for me to do would be to try to give you a sort of overview of how, of what my sort of early professional career was like, and a little bit, and how we got into organometallic chemistry, and then a few things about the rationale for doing organometallic chemistry, having been raised as a physical organic chemist. So the title is, well, maybe actually I can ask somebody to close that door. I think this will work a little better. Thank you. So the title reflects what I want to do today, which is to give you a sense of how a person trained in the study of organic reaction mechanisms even would try to, at least in the early 70s, when these two fields were really, they were basically serious silos. Why somebody would try to do physical organic chemistry on organometallic compounds. So I thought I would start by saying something about G. and Lewis, because as you'll see in a minute, I do think that there's a connection actually between Lewis and organometallic chemistry. And so I stole this from a website, and basically it sort of is a copy of some of Lewis's early notes written in a memorandum, I guess. I don't think this was actually published, when he was starting to think about how electrons were involved in chemical bonding. And he had this sort of interesting, now arcane idea that you could think about each atom as a cube, and you'd put together compounds, chemical compounds, by just generating concentric cubes. So some of you may have seen this the other times that we looked up Lewis's name. But it wasn't, so this was 1902, and it wasn't until the middle teens when Lewis came up with this idea that a chemical bond involved the sharing of two electrons. And that's what this says. Essentially, this idea of chemical bonding evolved in 1916. That's when he came up with this idea that a chemical bond is a pair of electrons sharing two atoms. There's a reference here if you're interested in that. The way this connects to organometallic chemistry is that this really was the genesis of the 8-electron rule for organic compounds. That is, you needed a closed shell to make stable compounds. And Irving Langmuir, who Lewis didn't get along with all that well, was a person who actually tried to extend Lewis's ideas. He spent a lot of time both extending and popularizing Lewis's ideas. And he wanted to extend it to transition metals and various inorganic compounds. And that's where the 18-electron rule came from. So it was really Langmuir who extended Lewis's ideas of chemical bonding into an idea of how you could predict what might be stable as organometallic compounds. So this is me. I figured if I was going to talk about the past, you had the right to know what I look like. My wife tells me I haven't changed at all. And a little bit of my background. As Doug said, he basically told you about most of this stuff, so I won't repeat it. But this is a picture that we taken at Caltech about the time that we started thinking about doing some stuff in organometallic chemistry. So before I tell you about the chemistry that got us into this, I need to give you a few disclaimers. So there's been a lot of talk about self-plagiarism. I'm sure many of you have heard of this. It basically means that, you know, you're not supposed to plagiarize stuff in a paper you're writing if even you have published it before. So you can't take an introduction, for example, that you've written and use the same wording. I think this goes a little far, but that's what a lot of journals are doing now. So by full disclosure, chemistry I'm going to talk about has been self-plagiarized from earlier talks. And this is a review actually that you might want to look at because it has a lot in it that I'm going to tell you about today. So many of the physical organic techniques described in this paper could represent the first time they were used to study organometallic chemistry or organometallic reactions. But I can't claim that for sure because of Stigler's law of economy. So what is that law? Steve Stigler is a professor, actually a statistician. We went to Carmel College together, it turns out. And he's become a very well-known statistics professor at the University of Chicago. And Stigler's law of economy says no scientific discovery is named after its original discovery. So of course the problem is this has to apply to Stigler's law. And Stigler understood that. And he said that Robert Newton was the real discoverer of Stigler's law. Okay, so how did we get started with all this? It may seem strange, but this now simple thermal reaction, I will try to show you how it led us by a kind of circuitous route into studying organometallic chemistry. These molecules are called enedianes, and in the late 60s and early 70s, we were interested in finding and synthesizing molecules that had structures that were relevant to an area called non-benzenoid aromaticity, and non-benzenoid anti-aromaticity. So one of the things we were interested in was trying to generate molecules that look like this. So you can think about this as benzene with two of its hydrogens missing. And that's why it's often referred to as parabenzyne, because if you take two hydrogens off the orthocarbons of benzene, you get what's called benzyne or orthobenzyne. That's a well-established intermediate. We wanted to make the para one. And a lot of people have tried to do this by sort of conventional means, by taking halides and eliminating them. Conventional ways of putting double bonds into strained molecules. But it occurred to me that this molecule is actually an isomer of either of these two, and this is just an isomer of this one. And so I thought maybe that there was some chance that this is in equilibrium with one of these. Now, even though this is a relatively high energy species, it's inevitable that this will be higher in energy. So we needed a way to try to figure out whether there was a little bit of this stuff in equilibrium with the starting diacellulate. And so I had the idea that if that was happening, since these intermediates have higher symmetry than the starting material, if you could label one side of this molecule, for example, with deuterium, and it actually went to molecules like this, and they had a higher symmetry, they had a plane of symmetry going through the middle, then it could open in either way. They could open back to this direction, or they could open in this direction, and that would scramble the deuterium. Now, you know, I talked to several people about this, and they all thought this was so high, this had to be so much higher energy than this molecule. There was really no way that this could happen. The nice thing about graduate students is that, you know, they don't always believe that, you know, that what they're told, if you like. And so I managed to convince a new graduate student, Rich Jones, who hadn't yet talked to enough people about this, to try this experiment. And this was a little bit challenging because these kinds of molecules, they're small, they're highly unsaturated, they're really difficult to handle. But Rich was able to do that, and he was able to make this deuterated molecule. I won't bother you with how we did it. Actually, he really started with this one. And blow it through a hot tube at 175 degrees. He gradually increased the temperature At 175 degrees, this reaction actually, this rearrangement actually took place, and there was no detection of either of these species, which would not have been found which would have been found if some other way had taken place to strand bacteria, but wouldn't have been formed in this reaction. So that was the first piece of evidence that we could at least generate transient amounts of this pair of enzyme species, but we still didn't know if it was this or that. And that came out of trapping studies. And so we were ultimately able to carry out these reactions in solution. Even at high temperature, if you use a high enough boiling solvent, you can do that. And we found that, just to tell you quickly, that in toluene, it gave that product, in tetrachloromethane, it gave benzene, and in this molecule, which transfers, very good at transferring deuterium atoms to radical centers, it gave this species, once again, with deuterium localized in the positions shown. In methanol, it gave this mixture of materials, and if the bond had been formed here, if this was a real single bond, you might expect the OH group to add across the molecule, but instead it's the CH bond that adds, and that's really diagnostic of radical chemistry, and so that's what led us to the conclusion that this species was a diradical. So that's the conclusion here, and we believe that, essentially that central bond has a negative bond energy. For good reason, because to close it up, you're really going to have to sacrifice a lot of the delocalization energy of benzene. Okay, so that was the source of this result. And I'll tell you one, I'm not going to talk about much practical chemistry today, but I'll tell you about one thing that, this is just a reference to later studies. One thing that came out of this ultimately, which didn't happen until the 1980s, some people at I believe it was Bristol Myers, found that, and I think Casey Nicolau had some role to play because he was a consultant on this and he knew about the work that we'd done on amine dioxins. They found this natural product called calcimicin, which has amine diine in it. And what's more, it actually cleaves DNA and acts as an antibiotic. And the way it's supposed to happen is by effectively cleaving this disulfide, then the sulfur fragment adds to this double bond in basically a Michael addition. That squeezes down the ends of this molecule, and it makes the cyclization take place at much lower energy to give radicals of this type, which then undergo reaction with DNA by hydrogen abstraction from the backbone. So this is the presumed DNA cleaving mechanism of calcimicin, and they're now being used as anti-cancer agents. Actually, the conjugates with antibodies are being used as anti-cancer. And I guarantee you that if I had tried to get funding from the NIH for this, the first experiments that we've done, I certainly would have wound up with a priority way down in the and I think this is a good example of why fundamental research often leads in directions that are really hard to predict. All right, so what does this have to do with organometallic chemistry? Well, we had this stuff, this molecule in the lab, and Peter Vollmer had joined my lab again. And since we had this stuff around, and I was beginning to wonder about a lot of things in organometallic chemistry and catalysis, I was able to convince Peter to try going back to making these kinds of molecules, this one and this one, now complex to a metal, because there was some reasonable precedent that metal complexation would stabilize things that you couldn't isolate without the metals attached. So, Peter tried that, and we tried this reaction with cyclophenol cobalt dicarbonyl. This is a CP, is a 5-membered ring that often turns out in lots of organometallic compounds. And it didn't work. We got, very uncharacterizable material from this. So we decided to try this just to see if we could cyclize the 2 triple bonds with a carbonyl molecule, which had a lot of precedent in organometallic and synthetic organometallic chemistry at the time. We decided to try it without the molecule without the double bond here. This was pretty straightforward to make. And Peter found that it didn't do these things, but it made this interesting molecule, which if you sort of stare at it hard enough, you'll realize there's one dion here, there's another one here, and there's a third one here. So it's actually a trimerization. And it's also a trimerization that involves trimerization of 3 triple bonds. And that had some precedent in organic chemistry too. So Peter did that, he published it, and he took this kind of chemistry when he came to Berkeley. I hope I'm not speaking out of turn here, Peter, to generate some really brilliant extensions of this that led to a lot of really important total syntheses. Okay, so now we have a lot of this stuff around in the lab. You can see at the intellectual level at which a lot of our projects were started. And so at that time, I had developed an interest in trying to make transition metal compounds that were relatively nucleophilic. So the reason for that, there is some intellectual background to that, I guess, and that is that most of the organometallic compounds that have been made, and I would guess the large number of inorganic compounds at the time, were mostly in positive oxidation states. You know, they were metal 1, metal 2, metal 3, and so on. A lot interested in pushing that to making very highly oxidized species. But there wasn't much known about highly reduced metal complexes. The one sort of seminal experiment in that was Jim Coleman's discovery that you could take iron pentacarbonate and reduce it with sodium to make the tetracarbonyl dianion. And this thing actually showed reasonable nucleophilic properties at the metal. It can actually alkylate that stuff at the metal. And so we thought, you know, it's a pretty straightforward extension. The way this works is you take CO off and put two electrons in to replace the carbon monoxide electrons that are being donated to the metal. So the idea here was to do the same thing with cyclopentadienyl cobalt bicarbonate and see if we could make CP cobalt carbonyl 2-. Well, that didn't work either. But what did happen was the formation of this rather unusual dinuclear species with, which basically is a radical anion. So it was pretty hard in those days to characterize paramagnetic organometallic compounds, but we were able to do it because it was possible to crystallize this with what's called a phosphenimine salt counterion. I won't bother you with the structure of it. And that material has a very interesting ESR spectrum because there are 2 cobalt atoms with spin 7 halves, and that gives you a 15-line ESR spectrum. Believe it or not, that's 15 lines. The problem is that you always get these derivative spectra in electron spin resonance. So here's some data for that. The people who worked on this were actually able to crystallize this material, so we got an X-ray structure. It really does look like this. And what's more, you can alkylate it. And this was a very early example of a dinuclear compound with 2 alkyl groups, 1 on each metal. And there's still people interested today in trying to look for cooperativity between 2 metals to see if that cooperativity would do something differently than one metal could do. So we were interested in this. We want to look at its chemistry. You can get some of this double bonded species out as well because of the electron distribution here. And we could make a few different alkylated derivatives. So the idea was, is there some way you can take this dinuclear compound and form bonds either between the 2 alkyl groups or between the 2 alkyl groups and a molecule, some other unsaturated molecule like carbon monoxide. And if you think about the carbon monoxide reaction, you would basically say, can we transfer these 2 alkyl groups to one molecule of CO and make, for example, acetone or some other ketone with those 2 alkyl groups? And sure enough, if you take this material and treat it with carbon monoxide, it actually goes to acetone and generates more of the thing we started, the CP cobalt bicarbonyl. So a lot of people would have just done this, said, we'll just look at a whole bunch of different alkyl groups, see how many good ketones we can make and publish it. But this is where physical organic chemistry came in, because I was worried that even though it looks like you're connecting these 2 alkyl groups with CO in one molecule, maybe that isn't the way this works. And so my physical organic brain started to think about other possibilities. And one of the things we decided to do was this crossover experiment. Now, once again, I don't know if this is the first time a crossover experiment, which was quite generally used in physical organic chemistry, had been used in organometallic reactions. I should preface this by saying that most mechanistic studies in organometallic chemistry up to that time, there were some very good people doing this, one of whom was Jack Halpern, were mostly kinetic studies. And there were some beautiful kinetics done by Jack and other people, but other kinds of what I would call extra kinetic experiments were much less frequent. So we decided to try to check the idea that this was a straightforward intramolecular reaction by carrying out a crossover experiment. And sure enough, when we mixed, we carried out the reaction in a mixture of the undeuteurated and perdeuteurated compounds, where deuteriums and methyl groups, we got a basically statistical mixture of the D0, D3, and D6 acetones. So something more than just splitting out a ketone is going on here. So what is going on? Well, we also, we did some more experiments in which we just undertook the thermal decomposition of this material. Once again, if you don't add CO, you still get ketone in a pretty reasonable yield, and now you get both the dicarbonyl and clusters, because this is a CO deficient system. We've done that with the methyl, ethyl, and trifluoroethyl compounds, and what we found was the result of another kind of experiment that was very rare in organometallic chemistry. That is, we ran these reactions in NMR tubes and watched the NMR spectra as the reaction took place. And I should say that this was also not very traditional in organometallic chemistry. It wasn't even all that traditional in organic chemistry, but organometallic especially was a very synthetically oriented field. I hesitate to say shake and bake, but that was the terminology that was used in those days. People would, mix stuff together, and if something crystallized out, they often got a lot of pretty interesting compounds that way. And if things didn't crystallize out, there wasn't a good way, really, of figuring out what was going on in the reaction. So we were monitoring these reactions by NMR, and what we found was that in this case, the ketone wasn't the first thing that was formed. This mononuclear dialkyl was formed first. And with the alkyl groups, these were spectroscopically detectable, but we were actually able to isolate these things in the trifluoroethyl compound. I should say, by the way, just going back to this radical anion, this dialkyl compound was isolated by air-free chromatography on silica. Here's another thing that organometallic chemists didn't usually do, was to use chromatography to isolate anything. This was quite a challenge, because even though you can do the chromatography at room temperature, you can't let any air in. And so people were used to handling these molecules on vacuum lines, but combining a vacuum line with a chromatography column was something that was at least relatively novel, if not the first time anything done. Okay, so I just said that we had made this material. Now we know that from these results that the ketone formation can take place via the mononuclear intermediate. But here's another physical organic question that comes up. Again, someone might have said, okay, you can see this form, and you know it goes to the ketone, which we did. Then this must be the way the reaction is going. But the problem is that doesn't tell you about the kinetic competence of the species. So this is an example of, this brings up an example of what I like to call Halpern's law, because Jack Halpern was famous for an important study of catalytic hydrogenation, where he demonstrated that of a number of things that could lead to the hydrogenated product, the one that formed the hydrogenated product, the intermediate that formed the hydrogenated product, was there in lowest concentration. So I like to say that Jack's idea was that if you can isolate a material and characterize it by X-ray diffraction, well, if you can isolate a compound and characterize it by X-ray diffraction, it almost surely isn't the critical intermediate. If you can detect it, it could be the intermediate, but maybe not. And so the best evidence for an intermediate, in a reaction is not to be able to see it at all. So, this is sort of tongue in cheek, but to some extent it really reflects the way I think people, should think about this, which is that in order for something to take place, you have to make something in the middle of the reaction that's relatively reactive. Okay, so is this the intermediate or isn't it? Is it kinetically conjugate? Well, while we were doing this, we began to do some NMR experiments on the fluorinated compound. And we found an interesting thing. We put it in an NMR tube. It didn't have an NMR, at least we couldn't see it. That was at room temperature of 0 degrees. But if you cooled it down to 0 degrees and you look at it pretty carefully, you can see there's a peak there. If you lower the temperature even further, eventually a single peak comes up, a singlet comes up. At minus 50, it's quite sharp. There are a lot of possibilities for this. This is one thing that happens with conformational problems. But we believe that what is going on here, and this is all reversible, by the way, is that this is in equilibrium with a little bit of a 17 electron radical center. So, I mentioned the 18 electron rule at the beginning of all this. These are like 18 electron compounds. But one of the things that's important about the 18 electron rule is that things get generated from it, which often are intermediates in reaction. So if you lose a 2 electron ligand, that's a so-called unsaturated compound that's often important in a lot of reactions. But you can also break bonds to make radicals. So that's an interesting part of this because it's circumstantial evidence for what we think is going on that accounts for the crossover experiment. So we took this material and went back to the carbon monoxide experiment, only now we looked at it more carefully by NMR, monitoring it by NMR. And what we found was that it didn't just go to the ketone only. This diacetyl compound was building up in solution. So based on what we found with the fluorinated compound, we believe that this material, so by the way, this also happens faster than the dialkyl carbonyl goes to ketone. And that proves that this can't be the intermediate, even though it's formed in the reaction. So again, the kinetic competence issue raises its ugly head. And so this is going through some other intermediate other than this one, which we were lucky enough to see. So we couldn't pin this down completely, but we believe that based on this sort of accumulation of evidence, that this material, like the fluorinated compound, was in rapid equilibrium with the cobalt-17 electron radical, and then that reacts with carbon monoxide. There was good evidence that these 17 electron species underwent rapid exchange. So addition of CO could probably add to this to make a 19 electron species, or in a concerted reaction, the alkyl group might move over to do a carbon monoxide migration, or an alkyl migration, and that would give these acyl compounds, which are also 17 electron species. And now you can make 18 electron species by just transferring an alkyl radical from this acyl group to this radical center. And that makes an alkyl acyl instead of a dialkyl like this one. And it was known at that time that if you made an acyl group connected to an alkyl or a hydrogen, these underwent reductive elimination much faster than these did. And so we believe that that's the source, the source of the ketone. So that's really what this says. Okay, so this is a little lengthy description of this one study, but it reflects a number of the sort of principles that we were sort of bringing into organometallic chemistry or thinking would be useful in organometallic chemistry, even relatively early on. So I'll spend a couple minutes talking about this other reaction, which is a vanadium hydride reaction that looks like it could go the same way. That is one possible method. What we found was that this hydride reacted with alkyl halides to make hydrocarbons. So the possible mechanism for this is that this is, again, an anionic vanadium, so it should alkylate at the metal center, and then it could undergo reductive elimination to give this 16-electron vanadium compound, which would then be trapped by halide to give this final product. So the problem was that this didn't look like an SN2 reaction. So again, here's stuff coming from physical organic chemistry. It was true that iodides reacted faster than bromides and they reacted faster than chlorides, but it turned out that sulfonates were really slow. And normally they're very good substrates for SN2 reactions. What's more, primary, secondary, and tertiary halides all reacted at similar rates. And you could even get vinyl and cyclopropyl halides to react. Very unlike what happens with organic SN2 reactions. And the stereochemistry, and this was another rather challenging result. The stereochemistry of this, it basically gave racemic product. So in order to do this experiment in those days, we had to isolate enough of the deuterated compound to take its optical rotation, which was not simple since, as Judith knows, these things don't have very high rotations. That's the way things were done in those days. So it's racemizing, it's not going with inversion. And that is easier to see in these vinyl halide experiments where you get the same mixture from both of these compounds. So all of these observations are similar to those made in the study of the reaction of organic halides by trialkyl tin hydrides, which was a well-established radical chain reaction. So if you look at these experiments, you can see that these cyclizations were ones that had been used to study tin hydride reactions. We found that this material didn't cyclize very well with vanadium hydride. We got mostly just reduction of the bromide. But when you put an oxygen in here, because the radical with an oxygen cyclizes, and fast kinetic studies have established this, cyclizes faster. Now we got substantial amounts of the cyclized product, which occurs by having this radical center add to the double bond. So we believe that there's essentially a super tin hydride chain mechanism operating, because with tin hydride at similar concentrations, this gives a lot of cyclized product. And so we think what's happening is that some initiator abstracts the hydrogen atom from this vanadium anion, so it's a little counterintuitive. And then there's a radical displacement, that is, this vanadium radical abstracts a bromine atom to give an alkyl radical and the vanadium bromide anion, which is the 18 electron thing you can see. And then this material is the radical is what abstracts another hydrogen atom to give the hydrocarbon product, regenerating this radical, which goes around the chain again. But it means that because of the relative rates here, this radical reaction with the vanadium anion takes place at about 10 to the 7th per mole per second, which is an order of magnitude faster than what happens with tin hydride. Okay, time is running on, so I think what I'm going to do is skip this section and talk to you. I really want to say something about carbon hydrogen bond activation, so we'll come back to that if we have time. I'd really like to try to finish by 5 if I can. Okay, so we had found this result that Doug mentioned, which involved an iridium compound that was not actually the first time anybody had broken a CH bond with a metal, but it was the first time that you could see clearly a metal inserting into a carbon-hydrogen bond to give an alkyl hydride. And so after we published a few things in this area, Frederick Lafferty, a really important mass spec person at Cornell, got together with a bunch of other well-known people, as you can see here, and decided that they were going to publish an issue of Accounts of Chemical Research. I think this was I know there have been several of these now, but this was the first one that was called Holy Grails in Chemistry. And so Fred felt that Linus Pauling, who was alive at the time, was responsible for a lot of Holy Grails in chemistry, and that's what this is the introduction to that issue. That's what it basically says. And so Fred wrote to Linus and said, we're going to publish this Accounts of Chemical Research for Holy Grails in Chemistry, and here are some of the topics we're thinking about, one of which was CH activation. What do you think? And so Linus wrote his back. He said, "Dear Fred, I'm pleased you should write to me about a series of Holy Grails." I do not have any interest in any of the holy grails, which, if you knew anything about Linus, this is very typical. Followed by a text of what Linus was interested in. So it's his idea of holy grails. Okay, so this is the first part of the first page of our article, which summarized our work up to that time in hydrogen bond activity. So this is a little out of date, but for those of you who are Monty Python fans, you know that Monty Python and the Holy Grail is a pretty interesting movie, and if you haven't ever watched it, I would recommend it. And you probably can't read this. This basically came out of one part of the movie, and so I've blown it up. Okay, and you can see that it's basically, I'm not going to read this to you, but it's basically nonsense. And the reference here is, the people who played in the movie. Who I think also wrote the screenplay. Okay, so that was our little testimony to this whole Holy Grail. Okay, so what did we do? We had made this iridium dihydride, which hopefully you can see its modest relationship to the cobalt compounds we've been working with. And once again, we're sort of standing on the shoulders of earlier people, because Malcolm Green at Oxford had made some tungsten dihydrides and found that you could irradiate them, and the two hydrogens would come off in a reductive elimination. And they would generate a coordinatively unsaturated tungsten center, and that would do a lot of reactions which involved oxidative addition of various kinds, but they didn't react with hydrocarbon, saturated hydrocarbon. So we had this dihydride around for other reasons, and we thought, well, let's try Malcolm's experiment. And a really good student named Andy Janowitz, again, was willing to try this. And so he photolized this material with ultraviolet light, and again in an NMR tube. And if we hadn't followed this reaction by NMR, I don't think we would have discovered this, at least not as easily. Because what we found was that it was making very sensitive compounds. Something different was being formed. You could tell by NMR that some other hydride is being formed. And the key here was that we carried out the irradiation in different solvents. We got a different chemical shift in the hydride product. And that meant that there wasn't just an intramolecular activation of one of the methyl groups on the CP happening. So whatever was going on here had to involve the solvent. So we looked into it more carefully, and we did a lot of experiments on this. And once again, we finally were able to isolate the alkyl hydride product, I believe in the cyclohexyl case, once again by chromatography. And in this case, we had used low temperature chromatography. Things decomposed on both silica and alumina at room temperature. So it turned out that what we had to do was run the chromatography cooled with a jacket at low temperature, -80 roughly. And we had to do it air-free. So all of this involved essentially doing Schlenk techniques under conditions that you would normally just be able to pour stuff into a column on the bench top. Okay, it was the same time that Bill Graham and his coworker Jim Hayano discovered the same kind of reaction with this iridium dicarbonate and published it just after we did. So they really deserve credit for this as well. The really unusual thing about this reaction is that it's very selective for reacting with carbon-hydrogen bond. So if you do the reaction in cyclohexane, you get cyclohexyl hydride. If you do it in neopentane, you get the neopentyl hydride. If you do it in benzene, you get phenyl hydride. Methane reacts as well. So that was one of the few cases at that time when people could actually get methane to do these oxidative additions to give the methyl hydride. But the most sort of startling thing to me was that in tertiary butanol, which is materially soluble, if you carry out this reaction, it goes after it oxidatively adds the carbon-hydrogen bond, not the OH bond. And that was pretty much unprecedented. And so we did a lot of competition experiments to establish establish these selectivities. Another surprising thing was that primary CH5s reacted faster than secondary. They reacted much faster than tertiary. That indicated that this one couldn't be a radical reaction. I've already mentioned these heterohydrogen compounds. The other thing is that every organic solvent is reactive. So, we wanted to carry out kinetic studies on this stuff, and we couldn't find a solvent that would allow us to, vary the concentrations of things. We got really desperate when we decided to try liquefied noble gases, and so it turns out that liquid krypton and liquid xenon both work for this. Brad Morgan, who's here, knows that, for reasons I'll tell you in a minute. And so it turns out that liquid xenon, if you can condense it in an NMR tube at minus 60, it's a pretty reasonable solvent. It doesn't get in the way, obviously, in the NMR, at least not unless you're doing xenon NMR. And it's fairly hydrophobic, so you can dissolve, typically organic and organometallic things in it. So it's actually not so bad. And I've already said that this was inspired by these green experiments. And I should point out that these studies were carried out, experiments like this were carried out several years earlier by Bergman. And he never published them, and I think it's because he was following all his reactions by IR, not NMR. And he tried hard to isolate things and just wasn't able to do it. And so he told me all that later. And so I think he probably did these experiments a lot of the way he did. Okay, so we looked at kinetic isotope effects. I won't go into great detail except to tell you that when we do these isotope effects by competition, you can establish, for example, in a 50-50 mixture of cyclohexane and per butyl cyclohexane. But to get more of the protein stuff, the hydride with H instead of D. And that essentially establishes an isotope effect of 1.38. That's pretty low for a primary isotope effect, even for organometallic compounds. And that's what gave us our first hint that we were probably dealing with another kind of intermediate, which looked sort of like this, where the metal center was coordinated to the CH bond. And then that was formed first in what was at least either rate determining or partially rate determining step. And then over a rather relatively, finite but small barrier, it would go through the transition state to the oxidative addition product. And so that is a normal isotope effect because, we need to talk. I don't want to go into what's really happening here. I'm not sure this is right anymore, but I'm not sure how I can't remember how we were actually able to establish this was, okay, now I remember. So we can also do these reactions by thermolysis of this material. Let's say we start with the cyclohexyl hydride and carry out that reaction in benzene and get the phenylhydride. Those isotope effects are inverse because we believe there's substantial zero point energy in the transition state that isn't in the ground state in the thermal reaction. So that's why those reactions go that way. Okay, so these are the experiments that we did with Brad, and I have to acknowledge, basically say how grateful I am that he was willing to do this with us. We had a really good joint student named Dave Yeston, who some of you may know because he's an editor at Science now. And without again going into details, in this case we were able to actually observe spectroscopically at low temperature both the krypton. We're doing these in liquid krypton, so you can see both the krypton complex and this alkane complex. And that was observable, and there was a delay before it went on to the final oxidative addition product. So you'll see, you will probably notice that these two things doing these by following these reactions by infrared is much more informative structurally than following them by UV or UV visible. You'll notice these have the same IR absorption, so that made things a little tricky, but it turns out that they have different kinetic behavior, so we were able to sort out the fact that there were two different things because of the kinetic behavior. Okay, and then we extended that to a collaboration with Charles Harris, and we had to use a different ligand for these systems. But in this case as well, again, I won't go through this in detail, but we were able to see both the alkane complex. These are now, these reactions or these kinetic studies were now carried out on a deep record time scale. And we're able to see the alkane complex, one with this bridge attached, another one where we believe the bridge is detached. We don't see this intermediate because it goes to the oxidative fission product really rapidly. And so these are, this was a really important kinetic study that ultimately got published in Science. Okay, there's one other kind of CH activation that we've seen. Now, I should tell you that this is another collaborative project that Ken Raymond and I sort of got together and tried to do in just as a sort of simple conversation. We had found later on that iridium-3, which is 2 oxidation units higher than iridium-1, which is what is true for all the ones I told you about now, do these kinds of CH activation reactions, where essentially you lose a ligand, you get a 16-electron complex, and that goes after this aldehyde CH bond or other kinds of CH bonds, and ultimately goes through a series of reactions which generate this stable product. These were not only, for the first time, not decomposed by water, but the products were actually stable in water. Ken had been working with these cluster complexes, and so the question that we wanted to address together was, could we carry out these CH activation reactions inside the cavity of these clusters? It turns out to work. If these iridium-3 complexes are hydrophobic enough to be included into the capsule. You can see that by an arm. And they react with aldehydes, first to form complexes like this that we believe, and then ultimately through that series of reactions, they eventually split out methane and leave this final product, also encapsulated. And we've done a bunch of selectivity and cavity blocking studies that established that the CH activation reaction takes place inside the cluster cavity. So this was the first of what I think has been a very productive collaboration that ultimately wound up with a lot of catalytic studies in these systems. Okay, I think what I'm going to do is just wrap this up. I'm going to skip this one too. I always have way too much more to talk about than possibly. Sorry. And just tell you what I think we've learned from all this, and maybe some of the things we've learned, and I think take a couple minutes to do some acknowledgments. So these I would call it, most of what I've told you about, we've done a lot of kinetics, but most of what I've told you about are extrakinetic methods for investigating mechanisms that are not really typical of organometallic chemistry. And they've provided an important supplement to careful kinetic studies, which for many years have been the most important method for investigating inorganic reaction mechanisms. So much of what we've done in those years were focused on stoichiometric transformations, but those studies have provided important groundwork for more modern developments in both homogeneous and heterogeneous catalysis. There's surprising mechanistic similarities between organometallic reactions and a lot of organic reactions. So I haven't really had time to tell you about these dihydroxyl alkene additions. They turn out to look a lot like so-called quick reactions. Hydride transfer reactions, we did talk about the radical reactions that work with the Canadian hydrides. And CH bond activations, which will look a lot like carbene reactions. I wanted to say that collaboration with colleagues, and I hope I've made clear, at both Caltech, but especially Berkeley, has really been a crucial aspect of the progress that I've talked about. And then something I also mentioned earlier, very few of the studies in this talk were initiated or first rationalized on the basis of any potential practical application. And so I think that, for me anyway, this is an argument, especially the Einstein stuff, is an argument for really funding and taking seriously fundamental research that you can't tell right away what its practical applications could be. Okay, so first acknowledgement, sources of support. I really have to thank these organizations, especially the NSF for being willing to fund such fundamental work. Some other places that are important, including the places that I've been fortunate enough to work at. Berkeley has treated me incredibly well, and so I'm really grateful for that. My mentors were really important in my career. I worked for Jerry Bergman when he was at Wisconsin, and then he moved to Yale University, and I did a postdoc at Breslin. And sadly, both of these individuals died within the last couple of years. And as I said, I'd like to acknowledge my Caltech and Berkeley colleagues, as well as my administrative assistants. Annika is my current AA, and she's a wonderful person who does things that not only I don't have to do, but I really probably wouldn't know how to do. And other staff who have helped us incredibly in research and teaching. I have to mention my wife, Wendy. This is a picture that was a photograph that was taken in Israel a few years ago. It's probably easy to identify her, but I think I should point out that the camel is the one in the middle. And of course, last but absolutely not least, my coworkers that Doug made mention of. I've had a lot of really wonderful coworkers. Many of the ideas that I've talked to you about today came from them, not just the experimental work, but the insights, the ideas. We hashed out a lot of things, as I think many of you have, that made our work better than it would have been if we didn't have that kind of system. I'm not going to go through all of these. I'll just do this. There's like 3 pages of these. I'll do this quickly and give you a minute to see if you recognize. I'm sure you recognize some of the names. This is the next one. This is the next one. It's a little off the page, but I think you can see some of the people that I'm really indebted to. So I think one of the things that's important about this kind of thing, and I'm really grateful, I think, to Doug and whatever the committee was that selected me for this, because I think it's a great honor, and I hope I lived up to his amazing and kind introduction. But it's really important not to get too swelled ahead about things like this. So I thought I'd bring along this cartoon. It says, "Soldier, statesman, author, patriot, but still a disappointment." Thank you for sitting through this. Question.
If you had to pick one of your favorite ideas that never panned out.
Wow. Yeah, I'm trying to, you tend to block these things. I think looking for the metal, the highly nucleophilic metal anions, which, as I said, never really panned out, was one of them. I think that I wasn't able to, I didn't have time to tell you about the cobalt dinitrosyl chemistry. But that was a reaction where we took a simple cobalt dinitrosyl compound and we looked at its reactions with double bonds, and we actually formed compounds that had 2 new carbon-nitrogen bonds. So it was kind of the nitrogen analog of the Sharpless reaction. And we actually were able to find rather clumsy ways to turn those molecules into diamines, but we never were able to turn that into a catalytic reaction. The interesting thing about that is that the only way I could think of to do that was to basically, you make that dinitrosyl compound from nitric oxide. And so the only way I could think about doing that would be to have a small amount of the dinitrosyl with a lot of nitric oxide. And the problem is that nitric oxide is much more reactive than the dinitrosyl is, and just eat up everything, okay? It does terrible damage to organic compounds. So in a sense, what we had discovered was an anti-catalytic reaction, where we use the metal to moderate, to slow down the reactivity of nitric oxide. And then when you're stuck, you have to do that stoichiometrically. You can't do it with an excess of NO. So that was one thing that I guess would be in that category.
So Bob did mention that there is a reception outside. That's probably going to be a lot more comfortable for many of you. So why don't we adjourn to the outside reception, but first let's give Bob a round of applause.